This video we're going to talk about the electric field. And so the electric field is just a way to understand the electric force. So say we have our two charges Q1 and Q2. And let's make Q1, I don't know, a positive charge and Q2 will be a positive charge. And so we know that Q2 will experience a force going this way and Q1 will experience a force going this way because like charges repel. But the question is why or how? How do they know to repel? What tells them what to do? And so then electric fields are introduced to help think about that. So electric fields, and let's say this, electric charges produce electric fields. And my shorthand for electric field is a capital E with a little arrow on top. And electric charges in an electric field are acted on by the electric force. So what does it mean they produce an electric field? So all charges produce this thing called an electric field, and what it is it's like a modification of space around them in a way. So everywhere out here around this charge, if we're just looking at Q1, there's this electric field, and I like to draw it as electric field lines, and the arrows I have point in the direction that a positive charge would be forced if placed there. Right? So if I put a positive charge here, it'll be forced to the right. If I put it here, it'll be forced to the right. If I put it here, it'd be forced to the left. Right? And I also usually try to get the arrows to indicate that the electric field weakens as you get further from the charge. I'm not doing a very good job of that, but that's what I'm trying to do, right? So the electric field has arrows, and the arrows point in the direction that a positive charge would be forced if placed there. And the electric field gets weaker with distance. But basically this charge is there, and it lays out this electric field all around it. And other charges respond to that electric field, right? So if you are in an electric field and you're charged, you have to move. The electric field is what tells you to move, and the electric field is what extends through space. And so if we're just looking at what Q2 will do here, right? Q2 is in Q1's electric field, right? It's in a Q1's electric field, and it's a charge, so it will experience a force. So it'll be forced to the right. And the really cool thing about electric fields is that they're framed so that the electric force is equal to the charge, in that case it would be Q2, times the electric field at that point, wherever Q2 is. And then mathematically that means that, remember that the electric force is K, Q1, Q2 over R squared. Well, if Q times E is electric force, you can see that the electric field is equal to K times Q1 in our example over R squared, right? Because if we do this times Q times Q2, it'll give us the electric force. And so what does that really mean? Like what does K Q1 over R squared really mean? Well, this is just like acceleration due to gravity in a way. This is the electric force per charge. So what it's telling you is that Q1 has created this electric field all around it, and it gets weaker as you get further away. And what the electric field tells you is how much force should be put on you if you're a charge in that electric field. So if you're a charge and you're sitting in the electric field and the electric field is really strong, you experience a strong force. But the higher your charge, the higher the force, and that makes sense. And the smaller your charge, the weaker the force. Likewise, if you're at a point where there's a weak electric field, there will be a weak electric force. And I really think that this is best viewed visually. So definitely play with those two applets that I sent you links for. And hopefully that will help clear it up.